Today's lesson is all about slope. I'm going to start out talking about slope, and then Candace is going to follow me talking about slope, and Anne's going to finish up talking about slope. So in my part of the lesson, I'm going to begin by discussing slope between 2 points. And then I'm going to talk about slope of a line. And then I'm going to talk about differences between lines that have positive slopes, negative slopes, and zero slopes. Candace is going to do some graphical applications, and then Anne is going to finish up working with tables and some applications involving tables. So let's begin by talking about slope between 2 points. We're going to begin with a definition. If x sub 1, y sub 1, and x sub 2, y sub 2 are 2 points where x sub 1 does not equal x sub 2, then the slope m between the 2 points is defined by the formula m equals y sub 2 minus y sub 1 over x sub 2 minus x sub 1. Holy smokes, that is a screen full of symbols. Don't worry, we're spending the whole day on this topic. I think you'll be really comfortable with this formula by the end of the lesson. Before I start showing some examples using this formula, I want to focus on this letter m. You may be wondering, why on earth do we use the letter m to represent slope? So let's explore that question. Why m for slope? Well, the first issue I want to address is why we don't use the letter s. It's because s is a suspect variable. Now, what do I mean by that? Well, remember our talking about the fact that we like to cross our z's in math class? And the reason we like to cross our z's is because if we don't, it's easy to mistake a z for a 2, depending upon a person's handwriting. Well, we have a similar issue with the letter s. A lot of people's handwriting, the letter s looks just like the number 5. So to avoid confusion between the variable and the number 5, we generally don't use the letter s as a variable. It does happen from time to time, but in general, we don't do it very often. So let's get back to why do we use the letter m? Here's the answer. Nobody knows. Now, there are theories. For example, there's a French word, monter. It means to go up. Some people think that's the reason we use the letter m. There's evidence, though, that that's not really the reason. And the evidence, at least in part, is because the grandpappy of all of this graphical business, René Descartes, he was very French. And he never once used the letter m for slope. So a lot of people think that kind of disproves that theory. There's a Latin word, mons, that means mountain. Some people think, for some reason, that that's the reason we use the letter m. There's a math word, modulus. It means the essential parameter of determining, as in the essential parameter for determining slope. Some people think that's the reason we use m. I hope that's not the reason. Anyway, the bottom line is nobody knows. Now let's get back to that formula. What I want to do is I want to focus on the actual computation part of the formula. m equals y sub 2 minus y sub 1 over x sub 2 minus x sub 1, where x sub 1, y sub 1, and x sub 2, y sub 2 are 2 points. Let's apply that to the 2 points, 3, 7, and negative 2, 5. Here's our slope formula. So the first issue we have to decide is which is the point x sub 1, y sub 1, and which is the point x sub 2, y sub 2. You know what? Let's try it both ways and see if it makes any difference. I've created a little table here to help us keep track of which number is going to go for which symbol. So the first time I work this problem, I think I'll let 3, 7 be the point x sub 1, y sub 1, and negative 2, 5 be the point x sub 2, y sub 2. So my slope formula, m, is y sub 2 minus y sub 1 over x sub 2 minus x sub 1. Referring to my table, I can replace y sub 2 with 5, and I can replace y sub 1 with 7. I can replace x sub 2 with negative 2, and I could replace x sub 1 with 3. Doing my computations, I have negative 2 in the numerator, negative 5 in the denominator. The quotient of two negatives, the result is positive. So this is equal to 2/5. Let's see what happens when we turn our designation around. What if we made negative 2, 5, the first point, and 3, 7, the second point? Then we would have m, which is y sub 2 minus y sub 1 over x sub 2 minus x sub 1. This time, we would have 7 minus 5 in the numerator and 3 minus negative 2 in the denominator. This simplifies to 2 in the numerator and 3 plus 2, which is 5, in the denominator. The slope comes out to be 2/5. That's what we got when we did the points the other direction. So lucky for us, it doesn't matter which point we choose to be x sub 1, y sub 1, and which point we choose to be x sub 2, y sub 2. Let's work another example. This time, the 2 points are given on a graph. It looks to me like the point on the bottom is the point 2, 1, and the point on the top is the point 4, 5. I need to choose one of these to be x sub 1, y sub 1. I think I'll choose the bottom point. And the other point needs to be x sub 2, y sub 2. So I guess all I have left is the top point. I go to the old memory bank in the brain, and I pull out the formula, m equals y sub 2 minus y sub 1 over x sub 2 minus x sub 1. So looking at my points on the graph, I said that y sub 2 is going to be the number 5, minus y sub 1 is the number 1. And in the denominator, I've got x sub 2, which is 4, minus x sub 1, which is 2. So my numerator reduces to 4, and my denominator simplifies to 2. So I'm left with 4 over 2, which is 2. The slope between these 2 points is 2. Now I want to look at slope in a little bit different way. I'm wondering what kind of vertical and horizontal motions would I have to make to get from the point 2, 1 up to the point 4, 5. Well, one trick that I could take is I could start at the point 2, 1, and I could move vertically up first, and I would end up rising, if you will, 4 units. And we actually call this a rise. We say that the rise is positive 4. Now, to get over to the point 4, 5, I'd need to take a little run. 2 units right. We call this the run between the 2 points. So our rise is 4, and our run is 2. Let's look at our slope calculation. After we simplified the numerator and the denominator, we had the fraction 4 over 2. With our new names for 4 and 2, we could say that the slope is rise over run, where rise is y sub 2 minus y sub 1, and run is x sub 2 minus x sub 1. The expression y sub 2 minus y sub 1 is commonly called the rise between the 2 points. Positive rises indicate upward movement, and negative rises indicate downward movement. The expression x sub 2 minus x sub 1 is commonly called the run between the 2 points. Positive runs indicate rightward movement, and negative runs indicate leftward movement. We frequently refer to slope as rise over run. You're going to hear this phrase over and over and over as long as you're taking math classes. So here's another example. Let's find another point that creates a slope of 2 with the point 4, 5. So we're starting with the same 2 points that we had in our previous example. And when we started from the point 2, 1, to get to the other point, we affected a rise of 4 units and a run of 2 units. And we landed at the point 4, 5. So if we want to find another point that creates a slope of 2 with the point 4, 5, let's draw our rise over run diagram starting at the point 4, 5. Let's rise 4 units, run 2 units. When we do that, we end up at the point 6, 9. So the point 6, 9 must form a slope of 2 with the point 4, 5. Let's verify that with our slope formula. M equals y sub 2 minus y sub 1 over x sub 2 minus x sub 1. I'll let the 6, 9 point be the x sub 2, y sub 2 point, and I'll let the 4, 5 point be the x sub 1, y sub 1 point. Plugging in my numbers for my variables, I have 9 minus 5 in the numerator. 9 minus 5 is 4. That's the rise between the 2 points. I have 6 minus 4 in the denominator. 6 minus 4 is 2. That's the run between the 2 points. This is 4 over 2, which is 2. My slope checks. Now, something else that I'm observing about these 3 points is that they appear to lie on a common line. Let's get out a metaphorical ruler and see if we can get a little better judge of that. Yes, indeed, it does look like these 3 points lie on the same line. And it turns out when you take 2 points on a line and calculate the slope, it doesn't matter which 2 points you choose. You always get the same slope. This is pretty much the defining quality of a line. Now, we already showed that the slope between the blue point and the green point is 2, and that the slope between the green point and the red point is 2. Let's show that the slope between the red point and the blue point is also 2. This time, I think I'll start at the point on the top and work my way down to the blue point. So when I do that, I first make a significant drop. When you drop between the 2 points, we call it a negative rise. This specifically is a rise of -8. The value of y decreases by 8. Then I need to move left. When I move left, the value of x decreases, so we have a negative run. Specifically, we have a run of -4. And by golly, when we calculate our slope, slope is rise over run. So this is -8 over -4, which is 2. So let's focus on slope of a line for a while. Here's some facts, Jack. Lines have constant slope. That is, the slope between any 2 points on a given line is the same, regardless of what 2 points you pick. There is one exception to this, and the only exception to this rule is a vertical line which has undefined slope. I'm going to ignore that issue for the rest of this lesson, and we're going to spend a good bit of time on that on another day. I just wanted to get that out there so that it didn't seem like I was contradicting myself later on. So let's explore the idea of constant slope. I have a line here. Here's one point on the line. It seems to be the point 3, 6. Here's another point on the line. It seems to be the point 6, 4. So this is 3, 6. This is 6, 4. Now suppose I wanted to start at the point 3, 6 and do a rise over run that landed me at the point 6, 4. Well, the first thing I would need to do is I'd need to move downward. Downward is a decrease in y. Specifically, I'd need to move down 2 units. That is a rise of -2. I'd then need to move right 3 units. When you move right, x increases. So that's going to be a positive run. Specifically, we have a positive run of 3. So we see that the slope of the line is m equals -2/3. Now, I could have done the run part of the motion first and the rise part of the motion second. That's what's illustrated with this new slope triangle. What I'm going to do is I'm going to slide this whole picture up and down the line. And what I want you to observe is, as long as that orange point, the point at the top, stays on the line, when I go right 3 units and down 2 units, the green point is also on the line. Let's see that in action. As long as that orange point is on the line and I maintain this ratio of +3 for a run, -2 for a rise, I get a second point on the line. Now, -2 over 3 is not the only fraction that simplifies to -2/3. For example, if we had a rise of -4 and a run of 6, the slope would be -4 over 6, which reduces to -2/3. Let's see that on our graph. Again, starting at the top point, the orange point, I'm going to begin with a rise of -4. I've already gone down 2 units in this rise. Let's go down another 2 units. Then to make a run of 6, one way I could do that is I could make 2 runs of 3. And check it out. I have another point on the line. Let's think of another ratio that would reduce to -2/3. What if we had a rise of +2 and a run of -3? 2 divided by -3 is -2/3. So again, starting at the orange point, let's do a rise of 2, that's up 2, and a run of -3, that's left 3. Look where we are. We're at another point on the line. Let's work this example. Let's find 2 more points on the line that passes through the 2 points given in Table 2. And let's not use the same run in our 2 calculations. Let's begin by giving ourselves some room. So I'm given 2 points, and in my table I can see from the first point to the second point, x increases by 2. We call that a run of 2. I'm going to emphasize that it's a positive run. In my y values, I see that between the 2 points, y increases by 6. -2 plus 6 is 4. So we call that a rise of 6. And I'm going to kind of emphasize that it's a positive rise. So the slope between these 2 points, which is rise over run, is 6 over 2, which simplifies to 3. So let's think about some other ratios that simplify to 3. How about 3 over 1? Let's make a rise of 3 and a run of 1. So if we start at y equals 4 and we make a rise of 3, that's adding 3 to 4. Y is now 7. If we start at x equals 5 and we make a run of 1, 5 plus 1 is 6. X is now 6. Let's think of another ratio that simplifies to 3. How about -12 over -4? Let's pick up at this point 6, 7. Let's make a rise of -12 and a run of -4. 6 minus 4 is 2. 7 minus 12 is -5. We're now at the point 2, -5. Now, since each pair of these points produces a slope of 3, these points better all lie on the same line. Let's see. So there's my table of points, and I've gone ahead and shown that the point 3, -2 and the point 5, 4 were, in a sense, our starting points. Here's the 2 points I calculated. Let's see that they're on the line. So the point 6, 7, x is 6, y is 7. Yep, that's on the line. How did we find that point? We started at the point 5, 4. We made a rise of 3 and a run of 1. How about the point 2, -5? 2, -5. That's on the line. How do we find that point? We started at the point 6, 7. I think we could use a ruler here. We started at the point 6, 7. We went down 12 units. That's a rise of negative 12. And then we went left 4 units. That's a run of negative 4. Now I want to talk a little bit about the ramifications of positive slope, negative slope, and zero slope. Here's some facts, Jill. Lines with positive slope rise from left to right. We call these increasing lines. Lines with negative slope drop from left to right. We call these decreasing lines. Lines with a slope of 0 are level from left to right. We call these horizontal lines. Notice that all 3 of these references are made from left to right. You need to quickly train yourself to look at lines from left to right when you're thinking about questions about increasing lines, decreasing lines, horizontal lines. Let's plot lines with slopes of positive 4 and positive 3/2 that pass through the point 3, 4. Well, I need to think of some ratios that reduce to 4. 4 over 1, negative 4 over negative 1. If I start at the point 3, 4, and I make a rise of 4 and a run of 1, I'll have a point that makes a slope of 4 with the point 3, 4. Similarly, if I start at the point 3, 4, and I make a rise of negative 4 and a run of negative 1, I also will have a point that makes a slope of 4 with the point 3, 4. Let's get out our ruler and see that these points do connect to a line. Sure enough, they do. So here's our line with a slope of 4. How about a slope of 3/2? 3 over 2 simplifies to 3/2. Let's start at the point 3, 4. Let's make a rise of 3 and a run of 2. Let's start at the point 3, 4 and make a rise of negative 3 and a run of negative 2, because negative 3 over negative 2 also simplifies to 3/2. Let's get out our ruler. And sure enough, those 3 points connect to a line. The slope of this line is 3 over 2. 2 lines with positive slopes, 2 lines that increase from left to right. Lines with positive slope always increase from left to right. Let's plot some lines with slopes of negative 3 and negative 1/2 that pass through the point 3, 4. Negative 3, what's a ratio that simplifies to negative 3? How about 3 over negative 1? So I'm going to start at this point. I'm going to make a rise of 3 and a run of negative 1. Let's make another rise of 3 and run of negative 1. Let's go back to our starting point. Let's see, we want a slope of negative 3. How about negative 3 over 1? Let's make a rise of negative 3 and a run of positive 1. Look at these points. They connect to a line. So there's our line with a slope of negative 3. Let's draw a line with a slope of negative 1/2. Negative 1/2, let's see, we could do positive 1 over negative 2. A rise of positive 1, that's up 1. A run of negative 2, that's left 2. Up 1, left 2. Let's go back to our starting point. We also could have done negative 1 over positive 2. That's down 1, right 2. Down 1, right 2. Down 1, right 2. Let's get out the ruler and let's connect the dots. Cool. They connect in a line. The slope of this line is negative 1/2. 2 lines with negative slopes, 2 lines that decrease from left to right. Lines with negative slope always decrease from left to right. One last example. Let's calculate the slope of the line shown in figure 5. Looks horizontal to me. I think I'm going to pick 2 points on the line. Here's the point 2, 5. Here's the point 8, 5. So if I call this point x sub 1, y sub 1, and I call this point x sub 2, y sub 2, using my slope formula, m equals y sub 2 minus y sub 1 over x sub 2 minus x sub 1. This is going to be 5 minus 5 over 8 minus 2. That's 0 divided by 6. You know, if you have 0 pizzas and 6 people over, everybody gets 0 pizza. This is 0. The slope of this horizontal line is 0. Check it out. What's the rise between these 2 points? There is no rise in a sense. The rise is 0, actually. Y increases by 0 between the 2 points. Horizontal lines always have a slope of 0. So let's sum up what you need to memorize. And I mean you need to memorize this for life, because this is never going to go away as long as you're taking math classes. The slope of the non-vertical line that passes through the distinct points x sub 1, y sub 1, and x sub 2, y sub 2 is defined by the formula m equals y sub 2 minus y sub 1 over x sub 2 minus x sub 1. We frequently refer to slope as rise over run. Lines with positive slope rise from left to right. We call these increasing lines. Lines with negative slope drop from left to right. We call these decreasing lines. Lines with a slope of 0 are level from left to right. We call these horizontal lines. So Candace is up next. She's going to show you several more examples. She's going to work specifically with graphs.
In this part of the lesson, I'm going to look at interpreting slope from a graph. I'm going to start by looking at several examples where I'm going to give practical meanings to slopes. And then I'm going to end with a comparison of slopes. So let's start by giving practical meanings to slopes. What is the slope of the line graphed? Well, first of all, let's take a look at what we have here. My dependent variable, p, on the vertical axis represents population in thousands. My independent variable, t, on the horizontal axis represents time in years since 1980. I can see that this line is increasing. The line goes up as I look at it from left to right, which is how we read a graph. That kind of indicates that perhaps the population is increasing. Well, let's go ahead and compute the slope as we're asked to do. I should be able to pick any 2 points on this line to compute the slope. So what if I look at the point 5, 40, and the point 15, 60? To get from the point 540 to the point 1560, first I can move up 2 of these little boxes. But my rise isn't 2 here. I need to pay attention to the scale. And the scale on the vertical axis is 10. I'm moving up from 40 to 60. So my rise is actually 20. For my run, I also have to move, this time across 2 boxes. But again, I need to look at what is the scale on my horizontal axis. If I look at my horizontal axis, I can see that the scale is 5. I'm moving from 5 to 15. So the run is 10. Now when I go to compute the slope, I need to be a little bit careful. I want to make sure that I don't forget the units in my calculation. Slopes in applied problems always have units. So to find the slope, I'm going to look at the rise over the run. And on the graph, I've just labeled the rise as 20. I want to include units here, though. Looking at the vertical axis, my units are going to be thousands of people. So for my rise, I'm going to write 20,000 people. For my run of 10, to find the units, I need to look at the horizontal axis. And on the horizontal axis, my units are years. So my run is 10 years. 20 divided by 10 is 2, so I have 2,000 people per year. Now it shouldn't matter which 2 points I chose to compute my slope. Let's look at another calculation. What if I had taken my vertical intercept here, which is 0.30, and the point 540? Now if I look at my rise over my run, I have a rise of 10 and a run of 5. So when I go to compute the slope, I have the slope m is rise over run. So my rise is 10, and including the units, that's 10,000 people. And my run is 5, and the units there are years. 10 divided by 5 is 2, so I have 2,000 people per year. That's the exact same calculation I had when I chose a different pair of points. So it doesn't make any difference which 2 points I pick on the line, I should get the same slope. Well, what is the practical meaning of the slope? Well, we just said that the slope is 2,000 people per year. And I want to think about, what does the slope mean? So let's go back to the graph for a minute. My dependent variable p again represents population in thousands. My independent variable t on the horizontal axis is time in years since 1980. We talked about the fact that the line is increasing, so the population should be increasing here. And in fact, that's what the slope tells us. The slope, 2,000 people per year, means the population increases at a rate of 2,000 people per year. Let's look at another example. What's the slope of this line? Again, let's take a look at what it is that we have on this graph. If I look at the vertical axis, my dependent variable, v, represents the value of the car in thousands. If I look at the horizontal axis, my independent variable, t, represents the time in years since the purchase. This time when I look at the line, reading it from left to right, I can see the line is moving downwards. I can say the line is decreasing, or the value of the car is decreasing. That makes sense. After we purchase a car, the value goes down. So we're asked to find the slope. So let's pick a couple of points on the line and determine the slope between these 2 points. What if I take the point 1, 16, and the point 4, 4? Now when I go to find the rise and the run, first thing I'm going to look at is the rise, and I have to move downwards. So for my rise, I'm going to have a negative number. I move downwards from 16 to 4. So I move down 12, which I indicate with negative 12. For my run, I move to the right 3 units, from 1 to 4. So my run is 3. When I go to find the slope, I need to take the rise over the run. I'm looking at an applied problem, so I also need to take the units into account. So my numerical value of the rise is negative 12. Looking at my vertical axis, I can see that it's the value of car in thousands of dollars. So this is negative $12,000. My run of 3 has units of years, since my horizontal axis measures the time in years since the purchase. Negative 12 divided by 3 is negative 4. So for my slope, I have negative $4,000 per year. it shouldn't matter which 2 points I choose. So let's take a look at the graph again and compute the slope in another way. What if I chose 2 points right next to each other? What if I took the point 2, 12 and the point 3, 8? Well, what do I get from my slope if I take these 2 points? To move from the point 2, 12 to the point 3, 8, first I'm going to look at my rise. I move down 4 units, so I can say the rise is -4 because of the downward motion, and right 1 unit. So I can say the run is +1. When I compute the slope, rise over run, I have -4, this is in thousands of dollars again, over 1 year. -4 divided by 1 is -4. So I have -$4,000 per year. When I chose 2 points a little bit further apart, I also got -$4,000 per year for the slope. So again, it doesn't make any difference which 2 points I choose on the line, I get the same slope. Well, what's the practical meaning of the slope? We just found that the slope was -$4,000 per year. And now we want to think about, well, what does this mean? Let's go back to our graph for a minute. On the vertical axis, I have the value of the car in thousands of dollars. On the horizontal axis, I have time in years since the purchase. The line is decreasing, which tells me that the value of the car is decreasing. So we can say that the slope means the value of the car decreases at a rate of $4,000 per year. Let's look at another example. What's the slope of this line? Let's start by looking at what it is that's graphed. We have another applied problem. On the vertical axis, the dependent variable c represents the cost of the call in cents. So it looks like we're talking about some kind of a telephone call. And the cost of the call depends on our independent variable L, which represents the length of the call in minutes. I'm actually given a couple of ordered pairs on this line. So I think rather than just looking at rise over run, I'm going to go back to our formula for finding slope. We learned at the beginning of this lesson that the slope m is y sub 2 minus y sub 1 over the quantity x sub 2 minus x sub 1. But when I look at this graph, I don't see any x's or any y's. I need to change my variables to match with the graph. On my graph, my dependent variable on the vertical axis is c. So those y's need to be changed to c's. My independent variable on the horizontal axis is L. So the x's need to be changed to L's. So let's change the y's to c's and the x's to L's. Then my formula becomes the slope m equals c sub 2 minus c sub 1 over the quantity L sub 2 minus L sub 1. So let's decide which way we're going to label the points. What if I make this lowest point, 248, represent L sub 1, C sub 1, and the higher point, 581, represent L sub 2, C sub 2. Then when I go to find my slope, thinking about units again, because we're still looking at an applied problem, I need to take C sub 2 minus C sub 1. The 81, the C value, represents the cost of the call in cents. So I'm going to say 81 cents minus C sub 1 would be 48 cents over L sub 2. Well, L is representing the length of the call in minutes, so this 5 is going to be 5 minutes minus 2 minutes. And when I do this calculation, 81 minus 48 is 33, so I have 33 cents over 5 minutes minus 2 minutes is 3 minutes. 33 divided by 3 is 11, so I have 11 cents per minute. Well, let's think about what this means in practical terms. Again, let's look at our graph for a minute. The cost of the call in cents is my definition of my dependent variable C. My independent variable L represents the length of the call in minutes. The cost of the call depends on the length of the call. If I look at my line from left to right, the line is going upwards. The line is increasing. So the cost of the call is increasing. One way that I can interpret the slope that I just found, though, is to say that the slope, 11 cents per minute, represents the unit cost of the telephone call. We can always think of slopes as rates of change, though, so we can look at this in terms of the cost of the call increasing. So to think of a slope as a rate of change, we can always, or almost always at least, represent a slope by saying the, and I'll fill in this blank in a minute, increases at a rate of blank. I'll also fill this in. So in our first blank, we put in whatever our dependent quantity is. We're thinking about our dependent variable on the vertical axis. And the increase at a rate of refers to the slope. So the cost of the call, we just said the unit cost of the call was 11 cents per minute. Another way we could have interpreted the slope is to say the cost of the call increases at a rate of 11 cents per minute. This means the same thing as saying the unit cost of the call is 11 cents per minute. Lines aren't always increasing, though. So when we think of a slope as a rate of change, we need a couple of different scenarios. Our second one, for decreasing, we can say the blank, again, decreases at a rate of blank. In our first blank, we're going to put the dependent quantity. The second blank, we need to be a little bit more careful. We actually need to take the absolute value of the slope. When we have a line that decreases, the slope is going to be negative. But when we interpret the slope, we need to look at the absolute value of the slope. That's what we did in the value of the car example. We said the value of the car decreases at a rate of $4,000 per year. Even though in our computation for the slope, we found that the slope was negative $4,000 per year. We've already said the value of the car is decreasing. That takes care of the negative. If I said the value of the car decreases at a rate of negative $4,000 per year, I'd have a double negative and it would actually be increasing. So whenever we're talking about a line which is decreasing and we're interpreting the slope in practical terms, we need to make sure that we say the dependent quantity, whatever that is, value of the car in this case, decreases at a rate of the absolute value of the slope. In this case, $4,000 per year. For my last example, I want to look at a comparison of slopes. So I've got a couple of advertisements here, and I'm being asked which company's sales are increasing at a faster rate. I see Zappa Real Estate and I see ABBA Realty. And when I look at these two graphs, it definitely looks like ABBA Realty shows a line with a steeper slope. So let's see if ABBA's sales are increasing at a faster rate than Zappa's sales. Let's look at the two companies individually. So I'm starting with ABBA Realty because this is the graph where the slope of the line looks steeper. To find the slope, I'm going to look at 2 points on the line. I'm going to look at 150 as my first point and 255 as my second point. So to find the slope, looking at the rise over the run, my rise, I go up from 50 to 55. My rise, we went from 50 to 55 for a rise of 5. And for my run, I'm just moving right from 1 to 2. So my run is 1. So for my slope computation, I'm going to take rise over run. I have an application problem again. I'm looking at an advertisement, so I want to pay attention to the units. So instead of just writing 5 for my rise, I'm going to look at the vertical axis and see what the units are. The vertical axis represents sales in millions of dollars. So my units are $1,000,000. So I have $5 million for the rise, and then my run is 1. And if I look at the horizontal axis, we're looking at number of years since 2000. My units are years, so this is 1 year. 5 divided by 1 is just 5. So I have $5 million per year. So it looks like ABBA Realty sales are increasing at a rate of $5 million per year. Well, let's compare that to our other company. Let's look at the Zappa advertisement. Here I have 2 of the points labeled for me. I have a point at 160 and I have a point at 390. If I move upwards from 60 to 90, then I have a rise of 30. Then if I move rightwards from 1 to 3, I have a run of 2. So when I look at the slope in terms of rise over run, my rise of 30 is measured in millions of dollars. I'm looking at the units on the vertical axis. So $30 million. And my run of 2 is measured in years. I'm looking at the horizontal axis, which says number of years since 2000. So the units are years. So I have $30 million over 2 years. 30 divided by 2 is 15. So this is $15 million per year. Zappa's sales are increasing at a rate of $15 million per year. We just looked at ABBA and saw that ABBA Realty's sales were increasing at a rate of $5 million per year. Zappa's sales seem to be increasing 3 times as fast. So which company's sales are increasing at a faster rate? When I first looked at the 2 graphs, I said ABBA's seems to have a steeper line. So perhaps ABBA's sales are increasing at a faster rate. Well, of course, in their advertisement, that's what they would like us to think, but we looked at the slopes and saw that Zappa's sales are actually increasing a lot faster than ABBA's sales. We need to be careful when we're watching the news, reading a magazine, reading the paper, that we pay attention to what our units are, how the graph is drawn, what the scales are. So, which company's sales were increasing at a faster rate? We already answered that, but let's write that down formally. Zappa sales are increasing at a faster rate. That's the one that we computed as $15 million per year. So Zappa's sales are increasing at a faster rate than ABBA's sales, even though the line on the graph for ABBA Realty looked steeper. So ABBA sales were only increasing at a rate of $5 million per year. So that's the end of this portion of the lesson. I now want to turn this over to Anne, who's going to look at slope some more. She's going to be looking at some applications in tables.